Thank you. Thank you very much, Samir. And many thanks to the organizers for putting together such a nice workshop. And I have to apologize because I have had heavy teaching duties this week. I could attend very, very few talks so far, but today luckily is a holiday where I am, so I can be there all day today. And I'm glad to be here. Of course, I would prefer to be in Japan, but well, this is what it is. As Samir said, I'm going to talk about a generic space of BPS states for K3 theories. This talk is very closely linked to the talk that Anne has given, so there are also some overlaps, which I hope are going to be helpful rather than boring. And I will put the emphasis on different aspects of the whole story, in particular, this notion of a generic space of states in conformal field theories in general, maybe, but in particular for K3 theories. And that's an enterprise which I find useful just in the context of studying conformal field theories. If we knew what the generic space of K3 theories really, what kind of structure it really has, then we would have made a big advantage, a big step forward in understanding K3 theories in general. But the whole project, as Anne has described, arose in the context of Mathieu Moonshine, actually, and you've seen this equation several times already. This is what we call the conformal field theoretic elliptic genus of K3 theories. So here's the explicit formula for that elliptic genus. And on the right-hand side, you see the decomposition of this function into characters of irreducible representations of the n equal 4 superconformal algebra, which is the relevant superconformal algebra here. So with the notations that Anne used in her talk, this function here would be called ECFT with a 2, because we're working with central charge 6 here. All right, and now, as Anne has explained, the mystery here is not only the decomposition that we're seeing here, which seems to leave a trace of the Mathieu group M24, but also the fact that this is really an invariant on K3 theories. And on the other hand, it is constructed from part of the partition function of K3 theories, which, as we all know, is severely depending on all the moduli. So even on a quite naive level, one can get the idea that maybe the fact that all K3 theories share this one and the same entity could have to do with the fact that all K3 theories share a lot of structure, including some generic states, some subspace of the space of states, which is present in all theories. It's a complicated concept and vague on this level, if I just say it like that, in particular, because as you have heard, the magic of having an invariant here has to do with the fact that there are cancellations going on. So even though the space of states of K3 theories clearly is strongly dependent on the moduli, it depends in such a way that we have cancellations going on. So maybe the idea is kind of a little bit too far-fetched. But it's an idea that, at least in hiding, has been underlying our conceptual approach to Mathieu Moonshine from the start. And I think that now we have quite some evidence that there is such a generic space of states. Actually, I can describe it mathematically. It carries an M24 action. It agrees with the M24 module that Terry Gannon constructed, but still we're not done, although we know really where M24 acts and how that space underlies or has to do with K3 theories or K3 geometry. The story is not closed because there are all these questions about vertex operator algebras that should underlie or that also should be present on such a module. So we're not done, but we have made considerable progress because we know that there is such a space of states. But clearly I have to give some explanation for it. So this is the plan of my talk. I will begin as a warm-up with really discussing this notion of being generic from a mathematical point of view. It's closely related, but not the same thing as being dense. So dense subspaces can be generic, but don't have to be generic. And it's also closely related to a mathematical concept which is not so well known, namely that of meager sets. So I will explain what that's about at the beginning. And then we will use that knowledge to start counting generic BPS states and K3 theories. We will notice that that's not so difficult as long as you restrict to Z to orbifold conformal field theories, where we've seen a lot of aspects of the story already in Anne's talk. But then when we try to count generic states and K3 theories, in general, a priori we're stuck because we don't even know what that generic theory might look like until we turn to geometry for help. So then I will spend some time, as Anne has promised, in discussing the geometric counterpart of the conformal field theoretic elliptic genus, because at least on first sight, that seems to be the root of success in order to understand how to get our hands at a generic space of states. And indeed, that will work, although we will have to take a little bit of a detour to get there. So there are a few red herrings on the way that I hope I will explain. But at the end of the day, I will be able to present to you how one can count generic BPS states for K3 theories in general, and that will produce the M24 moonshine module, however, only as a vector space and a representation of M24 and the n=4 superconformal algebra. So it doesn't answer all the questions that we have about Mathieu moonshine, but I think it's a good start. And most of what I'm going to say is really contained in this series of papers that I have written with Anne Taormina. So this is based on our symmetry surfing concept and joint work with Anne. And in addition, as she already promised, I'm going to spend quite some time talking about this work of mine, where I'm telling the world that it dawned on me what this generic space of states is supposed to be really in the context of K3 theories. Okay, so let's warm up and let's try and understand what the word generic is supposed to mean. Let's first agree on what dense means and whether we know examples of dense subsets. I think we can all agree that we remember that the rational numbers in the real numbers are dense, and so are the irrational ones. And that seems to be slightly unfair because, at least intuitively, we know that there are kind of more irrationals than rationals. And we can make that statement precise. Of course, the rationals form a countable set while the irrationals don't. But a more useful way of phrasing this is by bringing in the concept of being generic or non-generic. And indeed, I claim that the generic real number is irrational. And this is something that one can say, that one can put on a firm mathematical foundation if one uses the definitions that I'm giving for you here on this transparency. Whenever you have a topological space, you can define the notion of being meager for a subset of that topological space. And this amounts to the fact that Q, the set that we're looking at, can be decomposed into a countable union of sets. And each of these subsets Qn we require to be nowhere dense. So they must have an empty interior. That's definitely a property that the rational numbers have, because the rational numbers themselves are countable. So I can decompose the set of rational numbers in the reals into a countable set where each of these set of subsets into a countable union of subsets, where each of these subsets contains just one point, one rational number. And then each of the Qn will definitely be nowhere dense. So indeed, the rationals in the real numbers have this weird property, which is known in topology, but not so well known beyond, namely the rationals in the real numbers are meager. And then by definition, the notion of being generic is fixed to say that the complement of the set that you found to be meager is generic. So by explaining to you that the rationals are meager in R, I explain to you indeed that the irrationals in R are generic. And that's the notion we want to work with in what follows. Now, I want to apply this to conformal field theories, etc. And now I wiped something out that I didn't want to wipe out, I'm sorry. So the space that I want to apply this first, because there still things are quite intuitive, is the moduli space of toroidal conformal field theories, the well-known Narine moduli space, which actually Ida talked quite a lot about in her talk. And well, this is given by this Grassmannian here. And the way I read the Grassmannian is by saying that this is really the Grassmannian of unimodular lattices of a certain type. So this counts for us unimodular lattices of maximal rank. And I put them into a space RD plus RD. And by this, I mean that I'm working in a 2D dimensional real space, and I'm using a scalar product where on the first part of this space on RD, I'm using the standard Euclidean scalar product. The second RD here is placed to be perpendicular to the first one. And on the second one, I'm also using the standard Euclidean scalar product, just that I'm flipping all signs. So this way I'm getting space of signature D comma D with the usual metric. And I also have to say that this is supposed to be an even lattice and of maximal rank, 2D. And that looks all very formal to all the physicists in the audience. Of course, what I'm talking about is the charge lattice of a toroidal conformal field theory. And the charge lattice gamma uniquely fixes the theory. And now one has to argue that that's described by this Grassmannian, but this is not actually what I'm aiming at. Now I'm claiming that in here, we can find a meager set, which is very similar to the rationals in the real numbers, namely the following set, where I want to distinguish or want to pick out lattices, which have the property that they contain at least one lattice vector, apart from the origin, which has 0 contributions in this second RD here. So I'm going to write that out. Oops, in the second RD. So I'm going to write that out by saying I want the existence of a lattice vector of this form. I'm using this decomposition into RD plus RD in my notation. This is supposed to be a lattice vector, but non-zero, because 0 is always in there, and that's a bit boring. And I'm claiming that this is a meager set, and you can argue in a similar fashion to the way that I did for the rationals in R. Well, I should decompose this into a countable union of sets that are better behaved. And one way of doing this is to just first look at all possible lattices which contain a vector like above, but with length squared n. And now you have to convince yourself that this is actually a nowhere dense set. That's not so difficult because I've restricted the lattice that I want to consider two lattices which contain at least one vector inside a fixed circle in this RD here. And that will give you something that's nowhere dense inside the moduli space. So that's a meager set, and the complement of this set is generic. And that now translates to something that we know in conformal field theory, and I hope won't be surprising to anyone, but I've now formulated it with this vocabulary of being generic or meager. This translates into the property of toroidal conformal field theories that generic such theories do not contain any additional holomorphic fields besides those that are obtained anywhere, that are there anyway because of the free fields that enter in the construction of holomorphic, of toroidal conformal field theories, namely the free bosons running along the circles of your underlying torus and their fermionic superpartners. And then, of course, between these fields, you can always take derivatives, normal ordered products, etc. So there are a whole lot of holomorphic fields floating around in toroidal conformal field theory in general, but the generic one doesn't get contributions to the holomorphic spectrum from any vertex operators labeled by some lattice vector in here. So that's, I think, something we would have agreed on previously, but I'm just matching it with this notion of being generic or meager in topology. And another notion that's probably well known to most of you is the fact that this, of course, implies that the generic toroidal field theory is non-rational, because a rational toroidal conformal field theory is characterized by the fact that its charge lattice, in fact, contains a rank D sublattice of vectors like such. And if already the theories with just one such vector in the charge lattice are meager, then the same holds even more importantly, or even more clearly for the rational conformal field theories. Nevertheless, the rational CFTs within the toroidal theories are dense. That's also a quite well-known statement, and it's not contradicting what I said before, in just the same way that we consider the rationals inside the real numbers. The rationals are dense, yet they're non-generic, they're meager. And that's the same situation here for the toroidal theories. Here I've written for you another way of saying something similar, but taking a slightly different viewpoint. We could now focus on the spectrum of our toroidal conformal field theories depending on the parameters of the moduli space. And we could ask how many states are there at any given set of eigenvalues of our favorite four operators. So I want to fix a conformal weight on the left and on the right. I want to fix a Yuan's charge on the left and on the right. Just choose arbitrary real numbers and ask what is the dimension of the eigenspace, or what is the dimension of states in the toroidal conformal field theory where these eigenvalues are attained. And then you can ask how this dimension behaves as you change the parameters inside the toroidal conformal field theory. And we've looked at the special case here, and up to here, we've looked at the special case where one of these conformal dimensions was set to 0. I was actually looking at holomorphic fields, so the anti-holomorphic conformal weight was set to 0, and we noticed that generically the only contributions that we have there are those coming from the fields that are listed here. So generically, the dimension of that type of eigenspace is minimal inside the, as we go along the moduli space. So there are points where the dimension can jump upwards, where we do have additional holomorphic fields, but generically the minimal dimension is achieved. And that could be argued even before this, even without the song and dance about being meager or generic. You can always think of your linear algebra lectures where you were supposed to calculate eigenspaces and dimensions of eigenspaces, and the dimension of the eigenspace is, of course, tied to the multiplicity at which some polynomial, a characteristic polynomial, vanishes. And if you look at your characteristic polynomial and make its coefficients continuously dependent on some moduli, then generically the multiplicities of all the zeros of your characteristic polynomial will be like the minimum possible value in whichever space you're looking at. And that's really the statement that I'm making here. But we have good right to talk about generic properties here because it's really linked to the topological notions as explained. Okay, yeah.
In the statement about no holomorphic fields, is if X is a boson, is e to the I times momentum times X allowed or not?
Well, it's allowed, but it's not generically holomorphic. It's not generic. And here I have to say which of those vertex operators, we call vertex operators here in this context, which of these vertex operators actually contributes a holomorphic field. I have to ask what the charge vector looks like. And in order for the charge vector to be such that the field is holomorphic, I need to insist that on the right-hand side we have a 0. So that's exactly what I'm discussing here. So I'm asking, how often does it happen that in addition to the free bosons and free fermions, etc., in addition to that, can I generate a vertex operator which is holomorphic? And there I have to discuss these properties of the lattices.
Right. So those would not be generic. I mean, wouldn't be contained.
Those are not generic. Because in general, you have to put an anti-holomorphic contribution as well in order to get everything well defined in your toroidal theory.
Yeah, I just wonder if there is any ambiguity in this, because if you are at some non-generic radius which allows for fermionization, then this definition would allow for fermions. But those are actually like something like e to the ix.
Well, I mean, here I'm counting the fermions also as, I mean, fermions are allowed, but still this is non-generic. I mean, fermionization also happens non-generically. You have to tune to very special radii. And yes,
Right.
very good point. That's why I was talking about this slightly clumsy notion here of theories that have no additional holomorphic fields, instead of addressing rational theories right away. Of course, if I want rational, then I have to tune to very, very special radii. But here I've started with discussing theories where there's maybe just one radius in a 4 torus that sits at a value where you get additional holomorphic fields, like ones that can be obtained via fermionization. But that also just happens at very special radii.
Okay.
Yeah. Okay.
Thanks.
Okay. So now we know how to use these notions in toroidal conformal field theories. Let's start applying this concept to counting states in K3 theories. And the guideline here is going to be the elliptic genus, because that's the quantity that we really would like to understand better. So here I'm repeating a few things that Anne has already said. I'm using slightly different notations, and I apologize for that. So just like Anne, I'm interested in these special combinations of zero modes of your usual n equal to 2 or n equal to 4 superconformal algebra. And I'm calling them L0 top and L0 bar top, because these are actually the zero modes of the Virasoro field in a topologically twisted theory. So that's why I'm using this notation. But that's not that relevant for this talk. What is relevant is what Anne has already said. These operators occur in our definition of the elliptic genus, and here I'm recalling that definition again. From a conformal field theory point of view, what we need to do is we need to take the trace of this operator here, where L0 top and L0 bar top actually feature. And if we do this for K3 theories, and Anne has told you what we mean by that, if we do this for K3 theories, well, every K3 theory gives the same result when we calculate this particular trace. It gives this combination of Jacobi theta functions. As an example, we can consider Z2 orbifold conformal field theories, where we can actually reproduce this result quite immediately if you know what the partition function looks like, but Ida has told us. So for Z2 orbifold conformal field theory on K3, where, like Anne, I'm going to use this shorthand terminology when I mean that we're actually taking Z2 orbifolds of toroidal theories. These, like the toroidal theories, are uniquely determined when we know what the charge lattice is. And here I'm writing for you part of the partition function. This is the part that Anne called Z ns tilde, because that's relevant for calculating the elliptic genus. So she had the ns downstairs, I think, and the 2 upstairs. And it's given by taking this particular trace here. And it's relevant for calculating the elliptic genus because, in fact, what I'm taking the trace of looks awfully like what I had up here, with the only difference that I still have y bar to the j0 bar minus 1 in there. So this is really part of the partition function. It's at the end as tilde part of the partition function. And that's because we like to work in the Neveu-Schwarz sector rather than the Ramond sector. So you have to do some spectroflowing in order to relate that to the usual formula for the elliptic genus. But we went through this exercise, and this is what it is. And now if you are familiar with the toroidal conformal field theories, you will agree, at least roughly, maybe the prefactors and the exact indices and the theta functions you would have to look up. But I think you will agree that this part of the partition function should have this form. And you clearly see that there's something moduli dependent in here. And there's some part back here which has to do with the twisted sectors, but that's actually what we have. And again, I think Ida in her talk had a very similar formula where you can check. Okay, so now I would like to extract the elliptic genus from here, and that's an easy exercise. We just have to insert y bar equal to 1. But instead of doing that, I want to follow up on this idea that maybe we can reduce our attention to just a subspace of the space of states, a subspace which stands a chance to be generic, because this is too complicated. So Anne has already explained to you that this can be done because by means of supersymmetry, we can argue that the contributions to this trace, which come from states with non-zero eigenvalue with respect to L0 bar top, and I see
Katrin,
disconnected. Yes, I see I got
This
disconnected.
is
I'm very sorry. This will take a minute now. And that's what I was afraid of going to be happening. Let's see whether I can get this going. Nope. Oh, my tablet has frozen. That's of course bad. Not working. I'm afraid I have to close everything down over here, at least. And restart. Okay, I don't know why this is not working. I'm going to use plan B and just use the transparencies. I cannot write on them then, but I hope it's not going to be too disturbing. So some of what I wanted to explain won't come across like I planned to, but I don't want to keep you waiting, however. So we're going to use the transparencies now. And I'm hoping you can see them now.
Yeah, we can see them.
Okay, let's go to full screen. And we proceeded not until here. We proceeded until here. Okay, so that's where we were. And I was about to tell you that I want to now reproduce this thing here. Oops, sorry. I wanted to reproduce this thing here from that formula down there. I could go about and just insert y bar equal to 1, but I want to use this observation that Anne also explained to us, namely that all the contributions to the trace here cancel that come from states where the eigenvalue of the L0 bar top is non-zero. Can you see my cursor, by the way?
Yes.
Okay, brilliant. So then we do that. We can reduce to the kernel of L0 bar top over here, and we can do the same thing over here in the trace. And then I can leave out the Q bar to the L0 bar top part because that was actually killed right now. And by direct calculation, one can go about and just extract those contributions from here that have the eigenvalue 0 with respect to L0 bar top. And this means that from the sum that we took over the entire charge lattice here, we're now reducing to a sum where we only have the elements and the charge lattice where the right-hand side is actually 0. And that should look familiar because we looked at that previously when we talked about generic versus meager. So that's the equation you get. And from here now, it's very straightforward to recover that equation back there, again, by inserting y bar equal to 1. This term here will give 0 because the y bars there cancel, and these here conspire nicely to give exactly that sum up there. But now if we talk about generic versus non-generic, we also see that we get rid of everybody here, apart from one contribution, when we just restrict to those charge lattices where no non-zero vector obeys this condition here. So we already know how to calculate the generic version of this expression here, because we did that previously when we talked about topology. So generically, the expression that we just discussed, generically, this expression will be given like so, where just all the moduli dependence got lost. I'm still keeping the contribution from gamma equal to 0. That's this one, and that will drop out as soon as I insert y bar equal to 1. So this is a generating function for the space of generic states inside Z2 orbifold conformal field series. Well, inside this kernel of L0 top bar. That's actually what we're going to study next. And that's a space which underlies the elliptic genus in the way that I've described. So in my talk, I will denote by curly V, the subspace of this, you could say, topologically half-twisted model, if you like, because the kernel of L0 bar top is the space of states of a topologically half-twisted model obtained from your K3 theory. And in this space, I'm only interested in the generic space, in this generic subspace in the sense that I've explained. And this is the formula you saw in the previous transparency. I've just copied it out because it's very important for many of the works that I've done with Anne, because this teaches us precisely which states sit in there, and then we can start and find further properties for that space of states. So for instance, and Anne has explained that to you many years back, we already discovered that at level 1, there is a 90-dimensional subspace, which is part of the generic space of states, and it has some nice properties, which we got excited about. It's 90-dimensional, it decomposes into a sum of two 45-dimensional representations of the mature group M24, actually. And of the action of the mature group M24, we can recover an action of a maximal subgroup, the octet subgroup, via symmetry surfing, where we combine actions of symmetry groups from different points in the moduli space. To get this far, it suffices to restrict to symmetry groups of Kummer surfaces, which are induced from symmetries of the underlying tori. And these three rather small groups then conspire to give the octet group. And we thought that's already pretty good, because for the first time, we actually constructed a representation which looks like there is a trace of M24, and we reconstructed this representation inside conformal field series on K3. But then, of course, there's a downside, and there have been questions already in Anne's talk. This is not yet M24. We would like to include other symmetries, and that's technically very, very difficult, although we should get away with just the geometric symmetries. But of course, in this whole story here, we're severely using the beautiful structure of these Z2 orbifold conformal field theories. And as long as we stick to those, actually, this is the best one can get. I still firmly believe that someday we will add the final missing symmetry, but we haven't done this yet. And one word of caution, well, the 45 here actually comes about as 15 times 3. These are dimensions of representations of SU2. Each of these groups is a subgroup of an SU2, but then when you combine them, you have to be careful, and that's the twist that we have to implement and that we actually put into the title of this paper here. So definitely this is only true as a vector space, but not as a representation of the octet group here, where these numbers even wouldn't make sense. And then we were happy that there's additional evidence for the fact that our observations generalize, and I will get back to that in more detail later on. The beautiful paper by Gabardine, Keller, and Powell that Anne has also cited already. There's some evidence that our results generalize to all massive levels, and I will be more precise in what I mean by that later on. All right, so we were quite happy with the result then, but then of course it has the downside that we're really restricting to these Z2 orbifold conformal field theories on K3. And that space V here is not the space that we're really after. We're after the space of generic states for all K3 theories. So we want to impose more genericity assumptions. So the space is too big. It's a start because it should contain the space of states that are generic to all K3 theories, but we need to select some states from here. Not all of them can participate. And whether it makes sense to talk about even selecting states in there, we have to discuss, and we will. But well, we're actually stuck at this point a priori, because we don't have any tools to access this generic K3 theory, because no such theory is known, as Anne has said. But there's help on the way when you turn to geometry. So what we now do is going to take a little break and look at the geometric picture of the story, because that, at least on first sight, seems to teach us what we need to do. And Anne has already mentioned there's a geometric counterpart to the conformal field theoretic elliptic genus. It's the complex elliptic genus. It's a mathematical gadget, invariant that you can construct actually for all compact, complex d-dimensional manifolds. And I like to view it as a refinement of the traditional Euler characteristic. So that's one way you can calculate the Euler characteristic. In this complex case, I'm just taking Z2 graded sum of Hodge numbers, or I can repackage things like so, where I'm repackaging the sum over J into this quantity, which is the holomorphic Euler characteristic of that holomorphic vector bundle. It's the kth exterior power of the dual of T. And this is a useful repackaging because I don't want to go into detail, but the properties of the holomorphic Euler characteristic are much better than those of the Euler characteristic per se. If you want to talk about genera in a mathematical way, then the traditional Euler characteristic is not such a good idea, but the holomorphic Euler characteristic is. And each of these integers here is an invariant of your compact d-dimensional manifold. Here I'm introducing a standard notation, which helps us writing things out. It looks a little bit illegal on first sight because I'm just pulling this letter chi to the left. I'm turning the sum into a direct sum because I feel a little sorry for those vector bundles who don't just want to be added. So I'm taking a direct sum, but I'm allowing decorations here by placing some integers in front of this. And actually, I'm going to be more general in a second. I'm even allowing to place some polynomials with integral coefficients in front of this thing here. So a priori, that's just a notation which you're supposed to read from right to left when I write something like this. In here, we have what we call a virtual bundle, and you can play with it if you want to calculate holomorphic Euler characteristics. This is the way you do it. And more generally, we have this notation where, as I already announced, we also allow to place polynomials, or in this case, monomials, in front of any of these gadgets here. So here I'm using x as a formal variable and introducing this virtual bundle. And if I wanted to calculate a holomorphic Euler characteristic of this, again, I would just pull chi past the direct sum and make an ordinary sum out of the direct sum in that process, and pull chi also past any of these decorations. And similarly to the exterior powers, one can also treat the symmetric powers. So that's a similar notation, and it's common in this context of introducing genera. And here now I wanted to write something on my tablet. I wanted to remind you of the fact that now this virtual bundle is in fact what I would call lambda minus 1 t star with the notation that I'm introducing here. Now, it's also a bit sad that we're losing all this information about the separate entities that I said are invariants here. The holomorphic Euler characteristic of any of these exterior powers is an invariant of the manifold M. And maybe I want to keep track of that. I could do that by introducing a formal variable y and replacing all the minus 1 to the k's in here by minus y to the k's. So instead of writing lambda minus 1 t star, I would write lambda minus y t star. And that's actually has been done. That's the classical thing to do. That's the Hirzebruch chi-y genus. And it just allows you to keep track separately of all of these integers, which conspire to give the traditional Euler characteristic as soon as you insert y equal to 1. And I'm telling you this because the complex elliptic genus I want to view as a refinement of the Euler characteristic. We've already refined the Euler characteristic now to the Hirzebruch-Chi genus, and now we have to take a huge leap and refine much, much more by making this virtual bundle actually quite complicated. And this is what we need. We need to wrap up the bundle that we've been happy with so far by decorating it with some prefactor and then tensorizing it with this horrible thing, which is actually a virtual bundle of infinite rank. This is an infinite power series. Think of this as expanding this as a power series in y and q and y to the -1. And then you have a formal power series. Each of the coefficients is going to be a complicated vector bundle made out of exterior powers and symmetric powers of T dual and T, the holomorphic tangent bundle of your manifold. And again, here I wanted to write for you such a decomposition. Anne had it on one of her transparencies because she said the geometric elliptic, the complex elliptic genus, the geometric counterpart of our conformal field theoretic elliptic genus, is then such a formal power series in y, q to the q and y to the -1, where each of the coefficients is actually a holomorphic Euler characteristic of one of these bundles. So that's how you're supposed to read this equation here. And there were questions about that. Actually, this means that indeed every coefficient in that formal power series is some invariant on your manifold. It's just the holomorphic Euler characteristic of something that is not very natural because it's cooked up by expanding this bundle here into exterior and symmetric powers of T and T dual. And so far nobody has given like a pattern of making this pretty and saying why these separate coefficients should be interesting invariants of the manifolds. And Anne answered to that question by saying, well, if you insert special values, then you get back like the Hirzebruch signature or the A roof genus. And those are actually the interesting cases that you can indeed produce. So those are the ones where we kind of make use of those invariants, and in some sense also the only independent ones. So everything else can be traced back to what Anne has said. All right, so far this is a formal procedure where q is a formal variable and so is y. But now one notices that actually the would-be power series that I cannot write thanks to my tablet not playing along, that formal power series actually converges even if you insert complex numbers for q and y, as long as y is non-zero and as long as q lives in a punctured unit disk. So if you want to write q as e to the 2 pi I tau as we're used to, and if you want to write y as e to the 2 pi I z, what you get is a well-defined function in tau and z, and it's actually even holomorphic in these two coordinates. So that's the complex elliptic genus. I'm not declaring that I made sense of why one should use this weird virtual bundle here, but it is natural if you want to approach this from string theory, then you can ask whether it's possible to construct a Dirac operator on the loop space of your manifold. And when you do that, you notice everything is infinite dimensional, becomes a little bit difficult, but you can make sense of a regularized U1 equivariant version of an index of this Dirac operator, and in several quite straightforward steps, you will reach exactly the expression that I had on the previous transparency. So there's some content to what I wrote. Plus, this function actually has beautiful properties, at least if you're working on a Calabi-Yau manifold. So if the first Chern class vanishes, then what you have is a weak Jacobi form. The weight is 0, the index is d½ and you can work with the full modular group. So it has properties that are reminiscent of what we know about the conformal field theoretic elliptic genus. And indeed, in general, we expect the two to agree, at least in those situations where it makes sense. And that's the case when we're looking at a nonlinear sigma model on some Calabi-Yau manifold M, where we expect the two to agree. This can be traced back to the agreement of two simpler invariants. If you send Z to 0 here on the left-hand side, what you obtain is the Witten index, just a number. of your sigma model. On the right-hand side, if you send Z to 0, what you obtain is the Euler characteristic. You've seen that on the previous transparency. The Euler characteristic, as we have agreed, is just a Z2 graded dimension of this cohomology, the complex cohomology on M, while the Witten index is a Z2 graded dimension of this space here. You could view this as the space of states of a completely twisted, topologically twisted model of your K3 theory. And the fact that these two numbers that I now can't write should agree, namely the Witten index and the Euler characteristic, can be traced back to the fact that you actually expect these two spaces to be isomorphic. And you can argue that that is the case by observing that these BPS states here are protected when you perform deformations, for instance, a large volume limit. And in the large volume limit, you do expect the topological model to actually reproduce geometry, in particular, this one here. So that claim here is a vast generalization of what we can prove, at least on the level of string theory, for the Witten index and the Euler characteristic. But still, this equation does hold true, as Anne has said, in the case of K3 surfaces and K3 theories. And well, that has to be taken with a grain of salt, because part of the reason why the equation holds is because we defined our K3 theories so that this works. But definitely for K3 sigma models, we can say a little bit more. And we know as long as we're working with K3, at least this equation here holds. Now, given that we could trace back the identification between Witten index and Euler characteristic to an identification of the underlying vector spaces, shouldn't we expect that the vector spaces that underlie our conformal field theoretic elliptic genus on the one hand and the complex elliptic genus on the other hand, shouldn't these spaces also agree? So these spaces are, as we've learned, the kernel of L0 dot bar on the left-hand side and the cohomology of this weird virtual bundle on the right-hand side. And now it's really terrible that I can't write anything because I wanted to cross this out with a big red pen, because this is not correct. And that's a pity, because actually the right-hand side is quite well under control. There's a nice paper by Thomas Kreuzig and Gerald Höhn where they study this space in quite some detail. It can be equipped with the structure of a vertex operator algebra. And they did this in order to explain Mathieu moonshine, and they couldn't make it work. And at the time, everybody was puzzled, because it's very, very natural to expect that this is the space that should be used in order to explain Mathieu moonshine, but it doesn't work. And it doesn't work, well, not only because this identity doesn't hold true, the identity doesn't, or the isomorphism here already doesn't hold true, because we know that the left-hand side is dependent on moduli and the right-hand side isn't. But now you could say, shouldn't we reduce to a generic subspace here and then expect that the two are identified? But even that is wrong. And that was an insight that took me a long time to get to, but I think it's very, very important. So this is a beautiful thing. It underlines the complex elliptic genus, but doesn't serve in order to explain much in our conformal field theories, because this space, I don't know what kind of relation it should have to the space on the left-hand side. Definitely not a straightforward one.
Which is bigger? Which
Yeah?
is bigger?
Well, I'm going to say in a second, right here. So I already said that the generic space of states in here, of course, is smaller than that space in general, because of all these additional cancellations that we see in the K3 elliptic genus. But reducing to the generic space of states here, which I call H0, gives you a space which is smaller than the right-hand side. So immediately answering to your question. And this all looks very theoretical. I'm defining the generic space of states to be some vector space, some infinite dimensional vector space that injects into this kernel for any K3 theory, but not just as a vector space, as a representation of the full n equal 4 holomorphic superconformal algebra and the J0 bar, because all these operators we still need in constructing the elliptic genus. So this is a representation space, and the definition I'm giving is that it should inject into the right-hand side. And of course, I want to take the largest space for which this is possible. That's the generic space of states, a state space shared by everybody in the K3 moduli space. But one has to be careful because this injection might not be unique. You should think of this as a model which lives outside of the K3 theory and just mapped inside to it, similarly to what you may be viewing the n=4 superconformal algebra as. That's an abstract object, but it has a life in every K3 theory because there's a state created by every field in the superconformal algebra in your K3 theory. So it forms a subspace of the holomorphic states in your conformal field theory, but it's different for each theory. And there may be even several ways of including such an n=4 superconformal algebra at points of extended symmetry. So, and that's going to become much more visible later on, but it's an important point to make here. This inclusion might not be unique. And still, it's not very satisfactory just to talk about this space on this abstract level. We want to have a model for it, concretely constructed from K3 theories or from K3 geometry. And at the time when I was looking into the details of the space, I actually managed to show that the space has to agree with the Mathieu-Munschein module that Terry Gannon showed exists. So I already know what the representation content is, and I already know that M24 does act. And then almost simultaneously, Bai-Lin Song came out with a paper in 2017, preprint of a paper where he calculates explicitly the cohomology of the chiral de Rham complex on K3 surfaces. We knew forever that this thing is around. I said forever that this might be useful, but we couldn't really say how. But he actually calculated this explicitly in the K3 context, and that enabled me to show that the two are actually identical as representations of n=4 and J0 bar. So what is this thing? I'm not going to go into much technical detail. This goes back to mathematicians' work, Malikov, Shechtman, and Weintraub, who construct the so-called chiral de Rham complex. And that's a mouthful, but for all string theorists, this should not be a scary notion, because what they actually do is they translate into string theory, into mathematics, what string theorists have been doing forever. They cover the manifold at disposal, let's say the K3 surface, with sufficiently small open sets, and on each open set, they work with 3 fields. We've been doing that in string theory forever. Being mathematicians, they don't want to deal with non-holomorphic theories. So instead of really constructing a sigma model, they work with the topologically half-twisted model from the start. And thereby they get away with just looking at holomorphic fields all the way through. So that's what this omega chi K3, omega chiral K3 is about. That's really realizing your string theory locally by free fields, restrict to the topologically half-twisted model. And then when you want to patch open neighborhoods, of course, we know how to do that. We know how to perform coordinate transformations. So that's all that's behind here. And then still you have to perform a cohomological construction because all these indices that we're looking at do live in cohomology. So then they're taking the cohomology of that. And this has an unexpected effect, but Kapustin explained that to us. This has the effect of kind of taking generic values, or in Kapustin's language, of taking everything to the large volume limit. And the way to make sense of a large volume limit is really mathematically to say, well, really we're looking at generic properties of theories. And I thought that this is the case for a long time, and that was kind of a little bit up in the air until Song actually calculated this thing explicitly, and I could show that this actually agrees with the generic space of states that I can recover from looking at generating functions and looking at minima of coefficients in the way that I explained on the first transparency. So that's that. And then because I have everything fairly explicitly in my hands, I can also prove that these are unequal. Actually, this guy here has too many holomorphic sections, so to say. So this one is really, really bigger than that one. And that's, as I said, disappointing because this is well studied. It's also a little bit surprising because these guys have a lot to do with one another. Just to give the keywords, this is a sheaf of vertex algebras, and that's the graded object of that sheaf. And that's the reason why on the level of cohomology, if you construct graded dimensions, if you construct Euler characteristics, the elliptic genus, the complex elliptic genus can be calculated either by using this thing or by using that thing. The result is the same. Nevertheless, no mathematician would have expected the underlying cohomologies to agree, because the cohomology of some complex of sheaves hardly ever agrees with the cohomology of its graded object. So that's why this inequality sign here is no surprise to a mathematician, but everything looked so natural over here. So actually I was a little bit disappointed. Yet it explains why Kreutzig and Höhn couldn't make sense of Mathieu moonshine while working on this thing, because we have to use this one. So hooray, we know what the Mathieu moonshine module is. Terry Gannon taught us what it is, but we also know how to construct it from geometric data on K3. We have to use the cohomology of the chiral-Durham complex. Still, we're not done because, well, there should be a vertex operator algebra structure on this, and we don't know how everything is compatible with the M24 action. So unfortunately, this is still a difficult object to treat. But there are some consequences to this. There are some consequences to this story, which are maybe more down to the earth. For instance, there was also some discussion about the n=4 enhanced superconformal algebra in Ann's talk. And by defining K3 theories, we start with n=2 superconformal field theories, and then we notice, oh, all of them actually have n=4 supersymmetry. Wouldn't it be possible that they have an even enhanced chiral algebra, all of them? No, that's not the case. And that's one of the side results that follows from knowing, thanks to Bailin Song, knowing explicitly what this space is. Generically, the chiral algebra of a K3 theory is just the good old n=4 superconformal algebra.
I have a question.
Yeah.
Is there a physical reason, or maybe you already explained this, but physically, is there an intuition as to why the VOA that Kreutzig and Höhn constructed on this on the EQ minus y, why that doesn't agree with the complex of chiral-Durham cohomologies on K3?
Well, very roughly, to explain what's going on, you need to use you need to use resolutions and so on. But very roughly, what's going on is that really the VOA structure over here is different from the VOA structure over there, because
Right.
what you do here in every step is kind of you truncate things and you project onto the various grades that you have, and that's not true over here. So to kind of have a compatible OPE on this side is much more restrictive than on that side, very, very vaguely. That's what's going on. So it all has to do with the VOA structure on both sides and how that translates into, the analytic properties that you know from geometry, where we multiply by just analytic functions. And we do want to have counterparts of that in the VOA language. And that's quite complicated on this sheaf. And over here, it kind of comes across over simplified, because that's just to put the name on the keyword onto the table. That's an OX module with x=K3, and this is not. So that's kind of the basic problem here. And again, it's yes, the main problem is that here in every step you project onto a graded piece, and thereby you throw away lots of things that be trouble and that are trouble, but that's wanted trouble because that's just there in K3 theories. So that's what's happening.
One more question. What would happen if you, or can one consider trying to use a different sort of a refined genus, not the complex elliptic genus or the Hirzebruch genus, but for example, the Hodge elliptic genus, that is also in some sense a refinement right?
Yeah, well, that's actually what I use here as a technique.
Oh,
I
that's
use a
okay, that's the thing in your paper.
I do some calculations, and that introduces, and there I introduce extra parameters to allow me to keep track of everything.
Okay.
So indeed, here I use a version of the Hodge elliptic genus, although again, there's lots of small print, and I'm noticing that actually I'm also running out of time. So I don't want to go into those technical details here, but yes, that's the right keyword. I'm using a Hodge elliptic genus here and actually generalizing a little bit from what was done in the physics literature. Yeah, that's the technique I'm using. Okay, let me try and continue. What now the task is let's get back to where we were. I'm excited that we have this generic space of states, but we still don't know how it sits in here. We have an intermediate step because we have the generic space of states of Z2 orbifold conformal field theories under control. But still, there's a question on how H0 sits in there. And well, we know what this is, but we want a selection principle and want to understand whether that even makes sense. And here, maybe this is helpful. How can I extract H0 from that generic space of states of Z2 orbifold conformal field theories? Theoretically, two possibilities. Either I have to do what Kapustin taught us, I have to take a large volume limit, but then I don't know how to do that because I don't know what the theories are when I change the volume. Or I perform deformation theory, and that's what was beautifully shown in the paper by Christoph Keller and Ayla Zadeh, where they perform deformation theory in exactly this setting. And so what happens is if you deform away from the Z2 orbifold conformal field theories towards a generic theory, this space here immediately drops to a smaller space, just a few states survive, and you immediately get the generic space of states. But this means that you cannot just go ahead and look at this space and earmark certain states and say, this one is generic, that one is not generic. It very much depends on which direction you perform your deformation into. The point here is that no matter which deformation you use, you will get the same representation of the n=4 superconformal algebra and J0 bar, but it sits differently in here. And so that's really a crucial thing to remember. But then if we want to really access the space and we don't want to go through the painful exercise of considering the chiral-Durham complex, then what we really need to do is take a certain example, to take a certain deformation and then see how under such a deformation the corresponding generic space sits in there. And that's what Anne actually explained to us in our joint work. We're using the deformation away from the Z2 orbifold conformal field theories, which goes into the direction of the diagonal twisted state. So it's democratic towards all twisted sectors, and that's wanted because we want to protect as much symmetry as we can in this process. And this is also part of the explanation for symmetry surfing, where we say, well, if we decide to keep different symmetries, then we can actually let different symmetry groups live happily together on this space of states. But how to exactly combine them and how to make this exercise work outside this Z2 orbifold context, that we don't know now. So I don't know, how much time do I have?
Well, you kind of exactly an hour from when you started, but there were interruptions and there were already some questions and also some technical difficulties. We have 15 more minutes for questions, so we can go on.
That should do actually in 15 minutes. I will wrap up a few things because some of this is also repetition of what Anne has said, but I'm putting it into the slightly different context.
Yeah, so maybe if you can leave 5 minutes for questions or so. Yeah.
I will try. Yes, thanks a lot. And sorry that I'm running out of time, but actually I'm getting excited about the topic, and that's a good thing. So now we want to address this generic space of states for the Z2 orbifold conformal field theories. And so far I've been very inclusive. Now I'm going to restrict to the massive states, just as Anne has explained to you. So this is what I call VBPS now. She had a curly H here for general K3 theories. I'm calling it V, for lack of a better letter, when I use the Z2 orbifold conformal field theories. And as you have learned, this generic space of states now by construction, when you split it into the irreducible representations of n equal to 4, then on the holomorphic side, all you have are massive representations. So these are the massive representations. I denote them by HL. And we have some multiplicities here. And then there's some remnant of the anti-holomorphic stuff, but this is just a finite dimensional vector space, which is responsible for introducing multiplicities, because we still have the J0 bar action. So this is actually a two-dimensional space of states with odd eigenvalue with respect to J0 bar. So when we later calculate a trace here, then this will contribute a factor of -2. And over here, nothing interesting happens. This is just C1 and will produce a factor of +1. And as Samir pointed out in Anne's talk, these coefficients here are in general severely dependent on moduli. Well, here I'm now restricting to the Z2 orbifold conformal field theory, so all of them are the same, of course. But if I lift this here away from the Z2 orbifold conformal field theories, then these coefficients will start depending on the moduli. But and we've known this forever as well, we get the coefficients that we all know and love in the K3 elliptic genus, the AL, those that keep a trace of the M24 action. We obtain them by just taking the trace, as I tried to say previously. We're multiplying by the -2 over here, that comes from there, and by the +1 over here, that comes from there. And we get this expression, and this expression is actually an invariant on the moduli space. So here you see on the nose that cancellations must be going on when you move away from the Z2 orbifold conformal field theories. And you also see who can cancel whom. These guys all should cancel something over here. So every cancellation involves one of these actually non-generic holomorphic fields. While over here, it's much less clear which of the GL or which parts of which GL will contribute over here. And we make use of the fact that we're looking at orbifold conformal field theory. So we know that the space splits into stuff that came from the underlying torus and stuff that came from the twisted sector. And here again, I'm decomposing everything into representations. That part is entirely coming from the underlying toroidal theory, and everything else is listed here, similarly to what Anne said. And here's in particular that subspace of the twisted sector built on the diagonal twist field and its orthogonal complement. And now here I can go quickly through this because Anne said all this already. In our older work, we actually took advantage of the fact that G1 invariant is 0. So when I want to look for cancellations, there are not so many options anymore at level 1 because we need to cancel this thing by something that comes from over here. And then we got really lucky because G1 diagonal actually agrees with 2F1. And so on the nose, we're kind of forced to say, well, probably these cancel. We looked into the fine structure of things and found then that on the V1 perp, we have this cool representation of the octet group. So that's how it came about. We're really lucky because the structure is condensed in where it seems to be sitting also in full generality, because this situation doesn't survive to higher levels. G1inf is hardly ever 0. But in this paper by Gaberty, Keller, and Powell, you see that actually VPerp carries the action of the octet group all the way through. And in fact, they also give an argument in terms of deformation theory, which we translate into the fact that we do expect VPerp to be present in the generic space of states all the time. So that's useful because now we have an upper bound and the lower bound for the generic space of states. BPS is an upper bound and VPerp is a lower bound, at least when we perform this deformation into the direction of the diagonal twisted sector, which is what we're reducing to here. And then in this really beautiful paper by Christoph and Ida, they confirm this expectation on level 1 by deformation theory. And what Anne has been explaining to you is our quest for a mechanism of how in this particular deformation, the selection of generic states or states that cancel each other would go ahead. And that selection principle seems to have to do with this geometric SU2 action, which she mentioned. So we construct a geometric SU2 action, and I don't actually know what the difficulties in reproducing the geometric version here are. What we really do is we're using the usual SU2 on C2. So SU2 will act on Z1 and Z2, the two coordinates of C2, just in the usual manner. So that's what I remember of this geometric action, but I might be missing a point when Anne says that she can't reproduce all of it, all of what we had then. So be that as it may, we checked this 100 times when we wrote the paper, so I'm sure that there's no problem in the paper, but maybe in the language, and in particular, this notion of being geometric, of course, is kind of overused, but we actually very, very concretely and explicitly say how the action is on every piece there. And we can prove, and that's not terribly difficult, that this SU2 acts separately on each of the ingredients in the game. It acts separately on the invariant part here, on the invariant part that sees vacuum representations on the holomorphic side, on the invariant part that sees massive matter on the holomorphic side, and the diagonal stuff on the twisted sector. And I want to emphasize, although this is a geometric action, we call it that, we do not expect it to extend in any natural way beyond these three spaces. So it's really restricted to these three spaces, and it's like a tool that should help us in selecting those pairs of states that can cancel. And what we claim is that the cancellation only happens between this part here. All of this needs to be canceled because all of this corresponds to non-generic holomorphic states in your conformal field theory. All of this must be canceled by stuff coming from here. Coming from here. That's our claim. And there's a rough argument explaining why one should expect that, because imagine that some of these would cancel some of those, then we would be working entirely in the invariant part, in the part that comes from the underlying toroidal conformal field theory. But then you should expect in the toroidal conformal field theory that there should exist a deformation which makes these things cancel. But that can't be the case because we're taking all states that are generic to all these Z2 orbifold conformal field theories, in particular those that live on the underlying tori. So that's a rough argument, but in more detail, what we discovered is that actually when you consider the SU2 action here and you decompose these guys into irreducible representations, all representations that occur here are odd dimensional, all representations that occur here are even dimensional. So if things are compatible with the SU2 action, cancellations have to happen here. So that would mean that this space is also part of the generic space of states, and that would mean progress. So I really have to notch it up now. So here's something for our friends in number theory who might want to help us in proving that this is a consistent claim. What I'm writing out here is the counting function for the states in here. I'm giving you the closed formula for that. We know that this formula, which contains the H2, H3, H1, and H4 that we talked about, we know, because we have the action of SU2 in our hands, we know that this can be decomposed into characters of irreducible representations of SU2 with integral coefficients. But we need to make sure that given any of these representations in here, which must be canceled, there are sufficiently many contained over here. So what we need to make sure is that all these coefficients are non-negative, and we tried to prove that analytically, but didn't succeed. We checked until I think up to order 100 over here, so we're pretty sure that it's true, because if you look at the asymptotics, actually the numbers become larger and larger, but we don't have a proof. So now I really have to stop, and this is my final transparency where I'm listing some open problems. There are many, and most of these problems I have mentioned anyway already, so I'm going to stop now so that there's still a little bit of time for discussions. So thank you for your attention.
Thank you very much for the nice talk. So we have a few minutes for questions.
There's something in the chat, I think. I can't really access it right now because I'm on full screen, but there seems to be something in the chat.
There's nothing in the chat, as far as I can see.
Okay. Ah.
So I had a sort of naive question. You had the statement that there is two Hilbert spaces which are not equal, and one of them is a subset of the other. Yeah, over here. Yeah. So I think I understand both sides, but I just want to understand it a little better. So the right side is some sort of formal sum of various spaces with coefficients being q and y, right?
Mm-hmm.
Yeah. So is there also q and y on the left?
Yeah, I agree. The notation is not terribly good here. Of course, I have to introduce the same grading over here, and that's understood. So I mean, I should have written that, but then I would have differed from the usual notation that Malikov, Shechtman, and Weintraub have. So the way I read this is that originally this is just a horrible infinite rank vector bundle, and I can kind of put order into it by using the grading that is taken care of, or that is kind of depicted by the q powers and the y powers. So this just gives me a hint on where which grades with respect to an action of an, it is really still linked to the underlying n equal to 4 superconformal algebra. Mm-hmm. So the powers of q count the eigenvalues with respect to L0 top, so the left partner of this guy here, and y corresponds to J0. And you have the same kind of grading over here. It's a very good question, because that's part of what Malikov, Shechtman, and Weintraub do. They actually start from this guy, and they show that there's an n equal to 2 super conformal algebra hidden in here. So in particular, we have an L0, it's a topological one. So in particular, we have an L0 top, and we have a J0. And J0 bar is somehow missing and not very present in these old papers, but J0 bar is actually hidden in the degree here of the cohomology. So that took a student of mine, Felix Grimm, which some of you have heard about several times, who studied actually this chiral de Rham complex as well. That took him a while to disentangle this from the old work, where it's somewhere there, but somewhere between the lines. So the J0 bar action, which in here is also hidden in introducing the signs, here is also hidden just in the degree of the cohomology on the left-hand side. So this is kind of in there, and it's kind of in there, and that's why your question is very good, as a graded vector space with a grading by L0 top and J0, and a Z2 grading by whether this is even or odd, whether the degree here is even or odd. Yeah. And only that ensures that when I calculate Euler characteristics on both sides, I get the same result, namely the elliptic genus.
And at a generic point, are these two the same?
No.
Not even.
No, not even. And that's something that's really, I mean, maybe at some point I should include 3 or 4 transparencies in a talk to really explain why going to cohomology, it's really the cohomology that makes things difficult here. When you take the cohomology of a graded object, you get more contributions than when you take the cohomology of just your sheaf, which is filtered. You need a filtration here, and that's why I needed these actions of J0 and L0 top that you asked about. So this is a filtered thing, but when you descend to the graded object, actually the results in cohomology change. And you can check that when you just look at a very short sequence, then one can see it on the nose, that there's no reason to expect the cohomology to agree. Mm-hmm. Yet you will agree that all this looks so similar. You produce from this expression here looks so similar to what we do in string theory. And I actually, for a very long time, thought that this is the space we need to look at. And I couldn't understand why Kreutzig and Höhn don't get the results that they should be getting. But that's a red herring. We shouldn't be using this space, unfortunately. has to do with the zero modes, of the three bosons in here, which are treated differently here and there. And that again translates into what I answered to the original question when I said it has to do with the action of analytic functions, because the zero mode wants to be a coordinate. So I want to build analytic functions from it. And the way that we multiply by these is kind of slightly different here and there. So that's really the difference between the two.
Okay, other questions? Yeah, we're, I think, now out of time, so maybe we should stop. Yeah, no other questions. So let's thank Katrin again.
Thank you for your patience.
So I think we can stop recording as well now.